Okay, so we'll get started. We left off last week. We kind of talked about the mechanics of doing hypothesis testing for proportions, either dealing with one sample or two samples. Okay, I posted some practice problems. There's a practice quiz number 4 on online under week 9. There's also a few additional practice problems. If they're going to be helpful in your study, you can use them. If you feel like you've got a handle on things, then that's great. And none of these things are required. I just put them out there to help you guys. We covered a lot of the mechanical aspects of doing hypothesis testing, and so now I want to spend today's lecture covering kind of a little bit of the conceptual stuff. Okay, so we'll talk about hypothesis testing, and we'll get into kind of conceptual things, and we'll review all of these conceptual things during week 10 as well, as we do some review for the final exam. Okay, so what we've established is that in the process of hypothesis testing, we go through the calculations to find a p-value, right? So steps 1 to 3, at the end of there we get a p-value. Okay, and so the definition of the p-value is that it is the probability of observing our data, or something more extreme, if we assume the null hypothesis is true. Okay, and so what this means is that if the p-value is large, then that means there's a good chance that our data could happen from random chance under the null hypothesis. Okay, and if the p-value is small, then that means our data is unlikely to happen while under the null hypothesis. Okay, and then if the p-value is small, all right. And so, and right now, the way we decide whether the p-value is large or small is that we compare it to what? We compare it to alpha, right? So what is large, what is small? We compare the p-value to our significance level alpha, our significance level, to decide if it is large or small. And so, we often use alpha equal to 5%. Alpha is often 5%. Okay? But it doesn't have to be 5%. We can choose a larger alpha. We can choose a smaller alpha depending on the context of the situation. Okay, and if we think about it, alpha equal to 5%, it's really just an arbitrary line. It's kind of an arbitrary line that has been established and has a kind of this history behind it, but there's not a whole lot of reasoning behind it, right? So, for example, we live with many arbitrary lines set up in society, and we just kind of accept them as they are. For example, when you are 18, you can register for the military and you can vote in elections and all of this, but that's just that's an arbitrary line. Okay, there's probably not a whole lot of physical or mental difference between someone who's 17 and 11 months old and someone who's 18 years old, but in the eyes of the law, if you're 17 and 11 months old, you're treated as a minor, and as soon as you're 18, you're treated as an adult. Okay? But we've also established arbitrary lines that are higher or lower depending on the situation. So for driving in California, that arbitrary line is lowered to 16, and we say at 16 we can trust you with a 10,000-pound vehicle traveling at 70 miles per hour, and trust that you will not bring harm to others. But society also says that we will not trust people until they are 21 to buy cigarettes or alcohol, because whatever, right? There's different reasons for these different decisions, and so depending on the situation, we might bring this arbitrary line from 5% to something higher, like 10%, or something lower to 1%. And so what are the reasons why we might want to raise or lower that? Okay, so let's talk about this. Okay, so alpha, the significance level alpha, tells us, tells us how willing we are to be wrong. Okay, how willing we are to make an error. Okay, and specifically, the significance level alpha is equal. Well, there's two types of mistakes you can make, and when it was first being developed, they could not think of good names for this, so they've called the first type the type 1 error. And then later on, we said, a better name for this thing is the false positive. Okay, but type 1 error has endured the literature, and it's still being used today. Okay, so the type 1 error, or the false positive, this is a mistake. Okay, and the mistake is that the null hypothesis is true. The null hypothesis is actually true. Okay, but our data and our conclusion, but our conclusion based on our data is to reject the null hypothesis. So it's not that we have done anything wrong in our process, but because our data is coming from random chance, our conclusion based on the data is to reject the null hypothesis. Oops, something happened there. And so that's a mistake, all right? Okay, so again, this is not that, it's not that we have done something wrong, okay? It's just because our data has come from random chance, it could lead us to the wrong conclusion, okay? So we did not necessarily do something wrong. I don't know how to spell, okay. Necessarily, we'll skip that. Okay, we did not do something wrong. I guess that's funny. We did not do something wrong, but our random data leads us to the wrong conclusion. Okay, so, you know, for example, when we were looking at the picture of the dog and the invisible owner, whenever we saw the dog, we said, oh, you know, if I see the dog here, there's a 95%, I'm 95% confident that the owner's within 2 yards of the dog or something like that. Okay? It's also possible that the owner was 3 yards away from the dog. And our conclusion about the location of the owner would be wrong. And it's not that we did anything wrong, it's just that when that picture was taken, it happened to be one of those times where the dog was far away from the owner. Okay? Likewise, when we're making conclusions about the population proportion P, you know, most of the time we're counting on the fact that P hat is close to the population proportion P. But because it's random chance, by random chance, we could get a P hat that is far away. And if we use that for our hypothesis test, we use that data, it could lead us to the wrong conclusion. Okay? And so, you know, we're like, okay, well, maybe I don't want to make this mistake, right? So if alpha is the probability of a type 1 error, can I just reduce my alpha so I minimize the chance of type 1 error? Okay? Yeah, we can do that. Okay? So if we want to reduce our risk of type 1 error, or reduce our false positive rate, we can just lower alpha. Okay. But the side effect of that is that if we lower alpha, we're going to increase the rate of the type 2 error, which I will have to describe. Okay, so reducing alpha to lower type 1 error rate will increase the risk of type 2 error. Okay, so what is type 2 error? Okay, so type 2 error, this is the, we might call this the false negative. Okay. The false negative, this is, in reality, the null hypothesis is false and should be rejected. But our data, for whatever reason, does not lead us to this conclusion. Okay, and so, you know, we conclude, do not reject the null hypothesis. and so that's the type 2 error. All right, so let me just kind of, we'll make a little table of kind of the reality and the outcomes, and I don't remember how the textbook does it, so if my chart looks different from the textbook, I apologize. Okay, so up here we'll put the reality. Okay, so in the reality, either the null hypothesis is true or the null hypothesis is false. Okay, this is the reality of our situation. And we have a decision, okay? Our decision, though, or our conclusion could be reject the null hypothesis or do not reject the null hypothesis. Okay, so if the null hypothesis is true and we have rejected the null hypothesis, what do we call this thing? This is the type 1 error. This is the false positive. Okay. If the null hypothesis is true and we choose not to reject the null hypothesis, what is that? This is the correct decision. Okay. If the null hypothesis is false and we have chosen to reject the null hypothesis, that is also the correct decision. Okay. And then if the null hypothesis is false and we choose not to reject the null hypothesis, this is called a type 2 error. This is our false negative. We put, if alpha is the probability of type 2 error, we have a symbol for type 2, alpha is the probability of type 1 error, we have a symbol for the type 2 error, and that is beta. Beta is the probability of type 2 error. And so to remember that, in the Greek alphabet, alpha is the first letter. It looks like an A. Okay, this is the first letter, alpha. And the second letter is beta. It looks like a B. Okay, so alpha for the first letter, beta for the second letter. Alpha for type 1, beta for type 2. That's actually where we get the word alphabet, is from alpha and beta just stuck together. Now you know. Okay. So type 1 error, this is alpha. Type 2 error, this is beta. Okay. And then 1 minus beta, this we give it a special name, and this is called power. Power is equal to 1 minus beta. When you do 1 minus a probability, what is that? It's a probability of the complement, right? So this is probability of not type 2 error, which, what is that? That's a correct decision, actually. So this is probability of not type 2 error. This is equal to the probability, so power is equal to the probability of correctly rejecting the null hypothesis when the null hypothesis is false. Okay. So you might say, well, do we have a name for 1 minus alpha? We do. It's called the specificity, but I don't know if it's not really it exists in some medical contexts, but power is usually the thing we go after. Okay, so let's talk about whether we want large alpha or small alpha and things like this, okay? All right. So imagine a criminal court case, okay? Criminal trial. Okay. And did you ever watch this show Cops on TV? I mean, it was on when I was growing up. It was on TV all the time, and I don't think it's been on the air for like 20 years now. But anyway, they just follow. It's a camera crew that followed police officers, and then they arrest people. But at the end of the show, they always said, everybody, suspects are always presumed what until proven. Presumed innocent until proven guilty in a court of law, right? And so when we set up our hypotheses could be that the defendant is innocent or the defendant is guilty. Which one should be the null hypothesis? Innocent is going to be the null hypothesis, okay? So the null hypothesis is going to be defendant is innocent. We presume this to be true until the evidence points us otherwise. Okay, and then the alternative is that the defendant is guilty. And it is the prosecution's job to present evidence to the judge and jury. To convince you that the null hypothesis is false and that the alternative is true. Okay, and if the prosecution doesn't have enough evidence, then the case will be dismissed, right? Okay, and so what we have here is, let's talk about the ideal situations, okay? Ideal outcomes. Okay, ideal outcomes is that if the null hypothesis is true, okay, meaning the defendant is innocent, ideally the jury will always conclude what? We'll always say not guilty, right? Notice the jury, when they come to a conclusion, they always say guilty or not guilty. The jury never says we, the jury, find the defendant innocent. Okay, and in the same way, when we do hypothesis testing, we never say the null hypothesis is true. We say we do not reject the null hypothesis. Okay, so the jury will always say not guilty, and I'll just write note. Jury never says innocent. Okay, and likewise, we never say null hypothesis true. We never say accept the null hypothesis. We say do not reject the null hypothesis. Okay. All right, and then the other ideal scenario is that if the null hypothesis is false, okay, meaning that the defendant is guilty, the jury always says guilty. Okay, and then we have two possible mistakes. Okay, which one is the type 1 error? What is the type 1 error? The false positive. So false positive for a criminal trial would be the null hypothesis is true, but the conclusion is to reject the null, right? So this is null hypothesis is true, but we reject null hypothesis. So that means defendant is innocent, but is convicted. But the jury says guilty. Okay, that's that is the type 1 error. The defendant is innocent, but the jury says guilty. All right. The type 2 error. What is the type 2 error? This is the false negative. This is the null hypothesis is false, but we do not reject the null. Okay, and so in the context of a criminal trial, what does that mean? That means the defendant is actually guilty. Defendant is guilty, but the jury says, the jury doesn't say, the jury never says innocent, but the jury says not guilty, right? All right, is that okay? Type 1 and type 2 error in the context of a criminal trial. Okay, so ideally we don't want either of these errors, okay? Ideally, we only want innocent people always to be acquitted, guilty people always to be convicted. That's what we want ideally, okay? But because we don't, because evidence can be destroyed or, we don't have all knowledge of everything all the time, okay? We might make mistakes, okay? And if we make mistakes, which of these errors is worse? Is the false positive or the false negative worse? And there's always some debate here, but if you had to set up a system, would you rather have more type 1 errors or more type 2 errors? We would want fewer type 1 errors, I think. Okay, at least this is how our American justice system is set up, and we say that it is worse to convict or sentence an innocent person to lifetime in prison or possibly execution than it is to let a guilty person go free. Okay, and I think sometimes we can probably think of some high-profile cases where we feel like a type 2 error has happened, right? A lot of these televised cases, without naming any names, sometimes these televised cases, as viewers, we feel like, oh man, this person definitely, may or may, whatever. Okay, and then at the end we say, oh, type 2 error, we feel that way. But that's just a natural consequence of the way our justice system is set up, okay? And so in this case, if we agree that type 1 error is worse than type 2 error, would we want a large alpha or a small alpha? Okay, so if type 1 error is worse than type 2 error, we want what, large or small alpha? Small. We want a small alpha. Okay, because alpha is the probability of type 1 error, and so if type 1 error is worse, we want to reduce this, right? Because alpha is equal to the probability of type 1 error. Okay, and they actually say this in court. They don't say use a small alpha in making your decision, but what do they tell the jury? That effectively says use a small alpha in making your decision. Beyond a reasonable doubt, right? That is the phrase that they use, okay? They don't want people coming to Reasonable doubt. They don't want people convicting someone because they just have a gut feeling that the person is guilty. They don't want people making decisions based on a hunch, but they want them to be confident beyond a reasonable doubt. Okay. All right. Now, I just want to illustrate this. They don't say you want to be 100% sure, though, right? What would happen if you had to be 100% sure? Okay, so being 100% sure would mean, if we, let's say, what happens if we use alpha equal to 0? Okay, meaning you will never commit type 1 error. Okay, if alpha equals 0, you will never commit a type 1 error. So let's say you're a judge, right? And sometimes you have to make a decision, guilty or not guilty. You are in charge of the sentencing, and one day you have this moral, ethical crisis, and you say, "Oh my goodness, I think I made a mistake in the past. I sent an innocent person to prison, and I ruined this person's life. I never want to make that mistake again." Okay, that's a reasonable thing to think. So you say, okay, I never want to make this mistake again. I want to reduce my alpha to 0. I never want to make a type 1 error again. Okay, what's the only way you can have type 1 error be 0 if you're a judge? Well, if you say, I never want to convict an innocent person, the only way you can absolutely be sure of that is to never convict anyone. Okay, that's the only way you can be sure that you will never convict an innocent person. Okay, because until you are in a position where you know everything all the time, which will not happen, the only way you can be sure that you've never convicted an innocent person is to never convict anyone. Okay, and if you never convict anyone, then you are not a judge. Okay, you are just a stamp of not guilty. And on the other hand, if you have the opposite dilemma and you say, well, I let an innocent person go free and I never want to make that mistake again, then the only way you can be sure of that is to convict every single person that shows up in your court, and you will be quickly removed from your post if you do that as well. So if alpha is equal to 0, the only way we can do this is, we will never reject the null hypothesis. Okay. We will never reject the null hypothesis, and then you're not doing hypothesis testing at all. You're just not rejecting the null hypothesis. Okay. You don't even have to look at data. You can just say, well, not guilty. And then on the other hand, so this would be the judge that never convicts. Okay, not really a judge, right? And then if we want to avoid type 2 error, we can increase alpha to be really high. Okay, and then this means we will almost always reject the null hypothesis. Okay, but this means this will result in a high type 1 error rate. Okay, so let's let me I'm gonna run out of time here. Let me throw you a clicker question at you, okay? And we'll decide what we have. Okay, so let's say you are a smoke detector company, all right? Smoke detectors, right? And so here we have a null hypothesis And an alternative hypothesis, the null hypothesis will be that there is no fire. And the alternative is that there is a fire. Okay. And the decisions will be do not reject the null, means stay silent. And reject the null will be sound the alarm. Okay, so what is this situation? Okay. There is a fire, and the alarm is silence. Okay, so your choices are type 1 error, type 2 error, or correct operation. So let's fire this up. It's working. Okay, so the poll has opened, and get your clicks in. There's a fire, and the alarm is silent. Is this a type 1 error, type 2 error? Is this correct operation here? Okay, I'm gonna close the poll pretty close soon here. Okay, so I'm gonna click stop. Okay, let's see. Okay, it's like 98% of you got it right. Okay, there is a fire means the null hypothesis is false. And alarm is silent means we did not reject the null hypothesis. So that would be a type 2 error. Okay. All right. Here's a follow-up question. Okay. In this scenario, we would want a large alpha, B, small alpha, or choice of alpha does not matter. Okay, so discuss.
That's the word. Yeah, but type 1 error is there's no fire and no experience. Type 2 error is the one that kills us. It's the one that we just identified as type 2 error. There's a fire. That's worse than there's no fire. If there is a fire, then you
Okay, I hear some good discussion here. Okay, I'm gonna click stop here pretty soon. So get your clicks in. Okay, I'm gonna go ahead and click stop. All right, so let's see. This one's a little bit more divided, and the correct answer here is alpha or A. Okay. All right, so let's discuss this. Okay, so in this scenario, which one is worse? Okay, type 1 error or type 2 error? Type 1 error. So type 1 error is false alarm. Okay, this false positive, false alarm. This is alarm, no fire. Okay. So this is like you burnt some toast, your alarm goes off. Okay, type 2 is fire but no alarm. Okay, so I think we would agree that type 2, this is worse. This is type 1 error is annoying. We don't want this, but type 2 error is potentially tragic. Okay, and so in this scenario, if we had to choose between making a type 1 error or a type 2 error, we would rather make the type 1 error. Okay, we would rather make our alarms overly sensitive and a little bit annoying than the other way around. Okay, than to have a, my mission is to make alarms that will never annoy you, but you might suffocate in a fire, and so that would be. I don't think people would want to buy that, right? So in that case, we would rather have alarms that are overly sensitive, and so we would rather have alarms that are overly sensitive than ones that are not sensitive enough. Okay, and this goes for a lot of times cancer detection. Okay, so when it comes to diagnosing or detecting cancers, it's much better to catch it early on than too late, right? And so women are supposed to do breast self-exams. Men are supposed to do monthly testicular exams. Okay, and you're supposed to do these every month. And if anything is slightly off, you're supposed to go see the doctor, okay? And you go on WebMD, right? And you say, well, something's wrong, and the WebMD says, oh, it might be cancer, right? It's the same concept here, okay? WebMD is just being responsible in having a large alpha. They'd rather you go to WebMD and say, it could be cancer, so you better go see a doctor, than somebody go to WebMD, say, I'm probably fine, I don't need to worry about it, and then it turns out that the person is actually sick, okay? So, there's a lot of jokes about how WebMD says everything is cancer. They're just keeping a high alpha so to make sure that you guys go see the doctor, okay? So here you go, large alpha, it influences a lot of our types of decisions. Okay, we'll see you guys on Wednesday.